Okay, so we have these sets of instructions. We're going to add, we're going to do an AND, we're going to do a load, an add, and then a store. All right, so our pipeline looks something like this. Great, let's go watch the first instruction. Initial state is no ops. Remember, no ops stood for no operation, which means that each of these pipelines are going to do effectively nothing, which is what we want in the beginning because we don't want to be changing the state any. Now, in order to make this at least somewhat interesting, I did give the register file some initial values in order to showcase the numbers. Otherwise, everything would be 0 at first and be a little boring. So the first one's the add. So we go and we fetch add 1, 2 into the instruction fetch / instruction decode. Notice the no ops are in the other stages. So this is at cycle 1. At cycle 2, we have the add inside of decode, read from register 1 and register 2. Great. And then at the same time this add, we are reading the and storing it inside of this pipeline register. So notice that we're already working on 2 separate instructions right off the bat, which is great. Next cycle, the and, or the add, is moved from decode into execute. We're going to go ahead and execute 36 plus 9, which is 45. While the add is being executed, the and is going through decode, or being decoded. And so let's see, 6 is 41, and then 5 is 7. So we're decoding that. We're writing to register 6, and it's an and instruction. And then while both the add and the add are being worked on, we're going to start our load word instruction. And so we just read that from memory and store it off. So again, we're now already working on 3 instructions at the same time. Next cycle, so cycle 4, previous was 3, the add, which was in execute, now goes over to memory. In the memory stage, we don't do anything, and that's perfectly fine. We go ahead and we just forward the values over to the next pipeline register. We do nothing with memory. But while add is doing basically nothing in memory, and is using the ALU to do the and of 41 and 7. We're storing that off here. And then move, we're loading from, let's see, we're going to write to register 4, great. We're going to read from register 2, that's the 9. And this 18 just kind of comes from whatever the bits are in there. So the move, or the load word, or the move L is being decoded. And while that's being decoded, we're reading our next add instruction here. So notice we're working on 4 separate instructions at time 4. At time 5, which is probably the most important time to understand, because that's when we're working, the pipeline is being fully utilized, and we're able to work on 5 instructions at the same time. The add is in write back, which means it's going to go ahead and update. Well, in this case, it was register 3. I think that's a slight error. It should be register 1. But we're going to just stick with that for now, because it's just for now. So the add is using the register file in order to write to, so that is the 5th cycle. The and is doing nothing in memory, because and doesn't do anything with memory, just being forwarded along. The move is calculating the offset of what was in register 2, which was 9 plus 20, so that's 29. The ALU is doing the address addition for you and storing that off. The add 5.2 is being decoded. So let's see, 5 is 7 and 9 is in 2, perfect. And then the move store word 3 plus 10, 7, so that's being loaded. Ooh, forgot to update that part there, but that should be a move S. So at this point, there are 5 instructions, and that's the most important thing to understand about this pipeline. They're each being executed on. Now we're going to just say no more instructions, so at time 6, the and has moved over to write back, and it's going to update register 6 with the value of 1. The move L, which is loading the value, is going to load from its address it calculated, which is 29. We'll just say the number is 99 that was inside of memory, just to keep things simple. The add is going to go ahead and compute, the 7 plus 9, which is 16, which is what I read from the register file. And then while that's happening, the store word is going to be decoded, and what we're reading from register 7, 22 right there. Ooh, that should have been up there. So these 2 numbers need to be swapped. All right. I said that wrong. No. These slides are correct. My apologies. We're reading from 3 because we are writing to register 7. Please ignore, scratch what I just said. We're reading from register 3. Slides are correct. It's 22, just from what the bits are, but the offset is 10, and we're going to write to register 7 for the store word, or the move S. Now we move along. Notice that the and was retired. The load word, the 99, we need to write to register 4, so boom, we write it there. We add. The add is in memory, it doesn't do anything, so we just forward the results along. And the store word needs to calculate the address, so it calculates 45 plus 10 to get the final offset of 55, move that along. The add needs to go ahead and write the result of, so it looks like 16 to register 5, perfect. And the move s, which is the store word, is going to store the value 22 instead of 7. So that's what that extra value was. That, oh, it was over here. That's why we loaded it from 7. That makes sense. And then forward it here in order to know that we're writing the value 22 into memory. And then right back for move s is nothing. So we executed those 5 instructions in cycle time of 9. If we look at the time graph, you'll notice that we each cycle takes 5 steps, but each instruction starts and completes one after another. And so the big question here, ignore that last slide, is here the CPI was 9 divided by 5, which is, what would that be, like, what was it, like 1.8 or something? But the question I have is, as the number of instructions increases and you're able to keep this up, if you're able to keep this up, what happens to CPI? Well, eventually your CPI gets closer and closer to 1, to where we just go ahead and call it 1. And since you were able to increase the clock cycle by a factor of 5, we'll just say for the sake of argument, because you chopped up into 5, hopefully even parts, your processor has had a significant performance boost. Okay, so we're going to go ahead and pause here for now because we did go through a good amount of material. Please go through and watch those slides again because it can get somewhat confusing. And make sure you understand pipelining, because we are going to go into at least the issues with pipelining and how we can resolve those issues on Thursday. One other thing I do want to mention is we do need to do a presentation for this class, and oh yeah, what's the let's see what our calendar looks like. Yeah, so Thursday we're going to yeah, so we're going to do, I'll talk about the presentations on April 13th, and then you're just going to have to turn them in. They'll probably be due on the, I'm going to have to make them due on the 30th because we do need a good amount of time. Alright. And those presentations are more of a little research presentation for everyone, edification. And their presentations, there's going to be both a computer science version and a security version, so you can go ahead and choose which one you prefer. Alright guys, so that is all for today, and I will see you on Thursday.